target. And so I have a number line here. Scales are arbitrary, so I don't really know this thing. And then, so the idea is that you give a number here called x, and the value of that like here, and we draw the arrow between them. So the idea of these mapping diagrams is to visualize the functions with these diagrams. And what they really are, is a way to visualize, in a much more effective way, tables. So we might have a table, and let's suppose that our function is kind of interesting, so not too interesting. Let's say minus x plus 1. That's not too interesting. And then we make a table, and I usually start top down 2, 1, 0, minus 1, minus 2. And then we've got, so this is 2 plus 1 is minus 1. That's going to go to 0. And then 1, 2, 3. Okay, so those are the values. And then the mapping diagram for that is going to go 2, 1, 0, minus 1, 2. And then we have values over here that are going to come up. 2, minus 1, 2, 3 here. Okay. So we just draw the arrows, and this is just transformation of this, transforming this information to a more visual format of the table. And the table is now organized. The right-hand side is organized in its usual order, and the arrows are telling us that 2 goes to minus 1, so let's start with this. And 1 goes to 0, and 0 goes to 1, and minus 1 goes to 2, and minus 2 goes to 3, and like that. And if I run that more accurately, the feature that looks like it's happening is actually happening. That is to say, all these arrows pass through the single point. All the arrows pass through the single point of this single function. And so the first example I have here is something like this, and then I would draw the graph to compare it with this mapping diagram as a way to visualize the information. And the graph of this thing is a line, and at 0 it's 1. And at this level, minus 1, so it looks like this. And I could put the data on that graph as well. Here. Like that. So it's just a different way to visualize. Now you can't, if you put too much of this on, it's going to get really nasty looking. But, you know, this is actually, this visualization, when the computer is drawing that visualization, it's actually filling in stuff and doing lines between the dots that only selects a small amount of the data and then does a line connect to the rest of the data. So you can put more of these on here. For linear functions, what's really important is this single point. That's what the mapping diagram is. It's a way to visualize functions. Very useful for visualizing functions, for especially for concepts that in this graph are hard to visualize, especially composition. Composition is very difficult for students to comprehend in the graph. They're very easy on the mapping diagram because you just take the next graph and paste them onto the next. So ideas about composition are much easier to get across, and inverses are also easy. You don't have to think about, oh well, the x and y, and you just go back to where you came from. That's the inverse. So if you want the inverse of this thing, you just push it back down here, and the inverse will take you from 3 to minus square that. You can't do minus 2. So this is the inverse of the first one. Deal with that quite easily that way. So the diagram has a lot of advantages, especially if you want to emphasize function concepts. The graph is very useful because it collects a lot of data, and it's easier to display the data much more quickly and all together, sort of, and give the illusion that you know all about the data, even though you've only really plotted a bunch of different line connects, even with the technology we have. This is a little more honest about the data that we're actually using, and you can put more of this. Now, if this thing were working, what I would show you is that with the current technology, this is actually has some very nice advantages. If you think about this as time and this is position, then you can, with GeoGebra or some other kind of graphic technology that allows you to take a point and move it on. You can actually take the point here, and you can grab the point and move it up. And as you move the point up the line, you see the arrows coming down the line at the same time. So you get the idea of the function is sort of time here and position here. And that's the way I like to think about functions. If I have two variables I want to model, it's time and position, which is the historic first way that function graphs actually started. If you go back to, say, Galileo in his view of how to visualize motion, there was time and position measuring the axis. So this is, I think about this as time and this is my position. For those variable names, but x and y are fine as well. Okay, so I have a little worksheet here. All right, so this is a typical beginning exercise for students that I give, where they fill in the table for a linear function, and then I'm giving them this values. They have to decide what the scale should be on the other side to get the range appropriately visualized, and then they draw the mapping diagram and compare it with the graph. So that's kind of, I'm going to go over there now. So that's the kind of exercise that I start my students off. And actually, the first exercise I give them the data and just ask them to plot the points and plot the arrows. Put the arrows on the diagram so we get used to the idea that there's a correspondence between the arrows and the points. So that's that. I wanted to see. So the next thing that would have happened. Anyone have a question about what the mapping diagram is? So the next thing I have here, which you can't see because it's not working, is a feature of the mapping diagram and the way the correspondence between a point in the plane and an arrow on the diagram. So if this point has, 1 minus 1, and this is 2, this is 1, 2, so that corresponds to 1, 2. So point in the plane corresponds to an arrow on the diagram. And similar, if I put an arrow on the diagram like 0, here's 0. Here's 0, or minus 1. So that corresponds to the point in the first point 0, second point minus 1. So arrows correspond to points. If I grab this point and move it up, it's going to move this point left and right. If I grab this point and move it up and down, it's going to move this point up and down. So the correspondence here is this is controlling left and right, this is controlling up and down. If you move this point around here, it's going to wiggle the arrows. So I have that all graphically illustrated in GeoGebra, not showing here, but it's really a neat feature, and a lot of students like that because they get to see the wiggle. They move this and they see the wiggle in the arrow, and they move the arrow and they see the point moving vertically and horizontally. So they get those coordinated a little bit better. It's like playing a little video game. And one of the nice things about mapping diagrams is that in the modern technology, you don't have to draw these points. You can do this dynamic thing and see the thing play it like a game. And you can enter the functions and it'll change the arrows right away. Just the same as you enter the function, you can change the graph right away. So it's very immediate. Quick.
Just as a question, you're saying all these fancy things, but you could do this, I guess, if you had something as simple as a spreadsheet.
Oh yeah. In fact, I'm glad you mentioned that because we have a spreadsheet here. Sure, yeah, it's on there. Okay. Well, I'm not going to go up with it right now, but every spreadsheet has these built in.
Right.
You make the table, and then you make the scatter plot, and all you do is change from rows to from columns to rows in the setting up of the scatter plot, and the graph fill in with the scatter plot becomes the mapping diagram. It's just that easy. So they all come up automatically with a spreadsheet. They're built in. Nobody knows it. Well, maybe you know it, but not many people know it. That if you change, when you build a scatter plot of a column like this, the first comes up, and there's a place where you have to choose, and it tells you what you're doing. You say, oh, there's a place where it says columns, and right above it says rows. You click that box off, list this box on, and rows. and then it's got a mapping diagram. This should finish it up this time. So it is already in the technology that's older, but not. This is not going to be dynamic in the same sense that I can move, drop a point like a can in GeoGebra, or Java general sketchpad, and just pull a point off. Yeah.
How does this mapping diagram detect discontinuity?
How would it detect discontinuity? You'd see the arrow jump. You'd see the arrow jump.
Oh, so you have to be watching it dynamically.
You see it dynamically. Yeah. You're going to see some kind of, whenever you see discontinuity, you're not going to see discontinuities on graphs if the discontinuity is not in one of the points, and it really is. So when you do a graph, and you look at a function like f of x is x squared minus 1 or x minus 1, when you look at the graph of that function, it doesn't note the discontinuity.
The mapping diagram doesn't know the discontinuity or the graph. The graph does.
The graph won't notice it. When you graph this function, you won't see the whole.
You just graphed a couple of points, it wouldn't have mattered. You have to know the discontinuity is at 1 for it.
Well, I mean, when you graph, you know the function is not defined at 1. So when you graph it, you skip 1.
Yeah, but I mean, you have to know that a priori. If you wanted that.
The technology, when you graph this function with the technology, you're not going to see a hole at 1. The only way you'll see that hole is if you actually put some kind of cursor that moves along the function, and when it gets to that point, it will go, no, not defined. But you won't see it on the graph because the graph uses a line connect between the data. You'll never see a hole here from this function.
When you use technology to graph something that has essential discontinuity, like y equals 1 over x,
Yeah.
the technology will not give you a value for 1 over x at 0.
Right.
But
This won't either. When I do it in GeoGebra, the table in GeoGebra will put an infinity at that point.
Right.
And when it gets to that point, the arrow will not come, there will be no arrow coming out at that discontinuity. But when you get close to it, you'll see the arrows zipping along way out here, and then way up there. There'll be a dramatic jump in the arrows, especially for an unbounded discontinuity. So it does have a powerful statement about that, about the hole there, that will be visible in the mapping diagrams. And when there is a discontinuity, when I draw them for students, and there's a discontinuity, I just go like this. I put tilt there. It doesn't get to the arrow, doesn't get to the other side.
That's your age. That shows you your age. You can't tilt anymore. That's for the old,
pinball machines.
Right, people don't play no pinball machines. They don't know nothing about that.
All right, well, anyhow.
You want to figure.
That's
404, put arrow 404.
Yeah, right.
Okay, arrow 404.
File not filed.
File not filed. Okay, so that's a good question, because the problems with discontinuities are hidden in the graph. They're illusory. You don't even see them, and which is a problem when you draw with the technology. When you draw a graph with the technology, you won't see the discontinuities unless they're unbounded. Otherwise, it's going to go right by you. So this function here is going to look like x plus 1, except it's 1, but it's not going to show you that unless you actually move along the data on the graph.
The other part of it,
Tracer.
the other part of it is smoothness, differentiability.
Differentiability, we'll get to that in a little bit. Yeah. Smoothness is a whole other story. Okay? And there's a way to interpret smoothness, which has to do with linearity, right? Because differentiability is local linearity. Okay? So understanding how linear functions work and how they look in mapping diagrams is crucial in understanding differentiability. All right? And a great example of that is if you want to understand the chain rule. All right? So you've got local linearity followed by local linearity. What are you going to do? You're going to multiply the magnification factors. That's the chain rule. So it's a great way to visualize the chain rule and to see the argument for its justification visually, which you can't do with the graph. The graph is just not easy. Students have a hard time with composition, even a harder time with the chain rule, and basically they throw their hands up and say, whatever you say costs, and move on. So this is I find this a tremendous tool for teaching, starting with, I start doing this in all my elementary functions pre-calculus courses. The whole course is based on doing both graphs and mapping diagrams for all the topics. Exponential function, log functions, trig functions, all have to do with mapping diagrams, and their inverses all work really nice. In fact, that's a material I'm working on this term. I'll leave this term, and I'm working on a book that actually, materials online that will visualize all this stuff. So, back a second. Okay, so, yeah. So I have online, maybe I should just get another file that has all this stuff. Online I've got, I'm working on a resource that has all this kind of material about how to visualize functions and these different features like continuity or right now linear stuff, the quadratic stuff, all is involved in all the little features you need. It has GeoGebra files or Sage files. If you use Sage, you know what Sage is. It's an open source thing. So it has Sage and GeoGebra, both little files that will pop up and draw the figure for you so that you don't have to reinvent those things for yourself. You can just use the tool in your classes. And it's going to start with beginning algebra and go all the way through differential equations. Right now I'm in transition to logs and exponentials and trig, which is a big part of trig, is a big thing. But eventually differential, calculus and differential equations. So let's see. So I think that's, let me say a word about this feature here, about the point here, because any linear function, will have a point like this. Now the negative exponent here is, so if I were to do, let's do 2x, I use the box as a fill in instead of putting an x there, I say 2 times whatever in the box, plus 1. So that's going to send 0 to 1, and 1 is going to go to 3. So there's actually a point associated with this linear function as well. The point is sitting back here. And this is a magnification by a factor of 2. So you see the quote y-intercept is the value of 0 is 1. And the magnification is this ratio of 2 to 1. And that's true no matter what interval you use for a unit interval. If you went to 2, it's going to be up 2 more. That's going to be 2 more of this. And it's going to go through this point and go there. So that's a simple geometry. I'm going to use that. I'm still going to use my outlines there. You don't need to see that. Okay, just give me more space. Okay, so this is so every linear function will have one of these focus points. That's what I call them, the focus point here. Focus point. Here, for negatives, it's going to be between the 2 lines. For positives, it'll be on this side if it's a magnification, on this side if it's a shrinking. Okay? And the only point you're not going to see is if it's x, because all those lines will then be parallel. And that means that the point where they all meet is out of infinity. And it could be infinite that way, or infinite that way. Because we want to close it broader about where infinity lies. Okay, so they're either, so the arrows are either parallel for linear functions, or which is when x is, when the slope is 1, the magnification factor, that's why I use m. It's not for slope, it's for magnification factor. So m is 2 here, and magnification factor 2 in the geometry is quite easy to understand why that's going to be the same from similar triangles. So mapping diagrams. Another feature about functions that's visually clear in mapping diagrams, if the arrows never cross, it's increasing. The function's increasing. If the function's decreasing, the arrows will cross. That's simple. So there's a visual clue as to whether it's increasing or decreasing. You don't have to think left or right, which is important when you talk about increasing and decreasing. In these functions, you have to think it's decreasing from left to right. It's increasing from right to left. But in the mapping diagrams, it doesn't matter left to right or right to left. It's just crossing and non-crossing. So there's no preferred direction in the analysis of the diagram to see whether it's increasing or decreasing. Okay, so that's this focus point. And you can use this focus point to solve some problems. So if you know the linear function already, so you found the focus point maybe here, maybe there. Okay, so suppose you have the focus point and you want to know what's the value at 5. Well, that's easy. Or let's take -1. This is a little easier. So you just go across here. And you read off, this is f of -1, whatever that value is on that scale. Whereas on the graph, you have to go up and then read across on the axis. Or read off, you have to estimate this. This is pointing right to the number. If you want to solve an equation like, okay, so when is this equal to minus 2? When is this -2? Okay, well you just take the arrow and you draw it to -2 and then you read off where it crosses. That's the value. So solving equations is visually clear, and it helps us understand, am I talking about a number that's an output of the function or a number that's an input of the function, as to how you do it. So it separates domain and target a little bit more clearly for the student, which is a little bit, I know when I was a student back Stone Age, that's when the stones were number 1. Tilt. So, we've identified that period. You know, somebody asks you a question, you have to think about, is it the second coordinate or the first coordinate that I'm dealing with? Is it a horizontal line or a vertical line that I'm dealing with regard to the graph? So this at least is always input, output, source, target, domain, codomain. It's always left and right. Now some people put these horizontal and vertical. I like them horizontal, both horizontal. I like them vertical because I can think about positions going up or above sea level. So that's why I think about it as moving objects above ground level. So I've got the cannonball in mind. Old stuff. Okay, so that's another way that the mapping diagrams can help you understand solving equations. And another thing about solving these equations is it focuses you on, there's a function that we're interested in when we solve an equation. And if you start thinking about functions, I remember going to a talk at the thematic meeting once, and the guy said the difference between the way we teach Algebra 1 in college and the difference and the way we teach Algebra 1 in high school is, when we do it in college, functions are important. And to make it a college course, we need to focus on functions, not just manipulating symbols to solve equations. So when you have a linear equation, like 2x plus 1 equals 5, that's really saying, when does this function give me the number 5 as the output? And so when you use these mapping diagrams, you can start refocusing attention on solving equations is about solving when a value comes out of a function. And then simple algebra is subtract 5 from both sides. You're always interested in when something is 0. Everything can be turned into, because of arithmetic numbers, everything can be turned into, when is something equal to 0? But we can visualize, 5 or something like this and see it as an arrow and focusing on 5 and come back and find out what it is. Okay, so solving equations for linear functions, all about finding the focus points. All right. Now, another quickie about the value of these things, before I move on to the deeper things behind this stuff, is inverses. So we give a function f of x is 2x plus 1. We put that up here already. So students learn how to find the inverse of this. They say, oh, call this y, switch the y's to x's, solve for the new thing, and it's a mechanical symbolic manipulation. Right? Now, here's a much, I think, more functional approach to this. First of all, this function 2x plus 1 is a composition. It's first multiple by 2, then add 1. Right? It's a very simple composition. And that's one of the things that is missing in most of the algebra up to pre-calculus is understanding that a lot of the functions that we're playing with, be it trig or logs and exponentials, that a lot of the play we give like 3 sine of x plus pi over 2, all right? That function is a composition. We don't need to think about, oh, you shift to the left, you multiply the scales, all that kind of stuff. It's a composition. And this is the simplest composition that is really helpful in understanding what's going on. Because if you think about this as multiply by 2, then add 1. So we break this thing down, it's actually first multiply by 2, then add 1, okay. First multiply by 2, then add 1. All right, that's the composition. So if we want to find the inverse for this, this is what people sometimes call socks and shoes. All right, so if you want to, first you put on your socks, then you put on your shoes. If you want to undo it, you take off your shoes and you take off your socks. Okay? So reverse of adding 1, subtract 1. And then reverse of multiplication by 2, divide by 2. So the inverse of this, I'll call it g. G of x is first take the number, subtract 1, and then divide by 2. First subtract 1, then divide by 2. You're just reversing the arrows. So if the students can get to that, it's a very simple concept here. And the inverse is not made by any kind of symbolic manipulation. Change the y's to x's and solve. It's functionally connected to the original function, and we're getting this really great idea about inverses reverse order. So we're just going back this way and back this way. And the focus point is out here at infinity, and out here, the focus point is over here. Because we're reversing the arrows, we're just going back to the original focus point. Just reverse the arrow. So the focus points come into play again. It's all a very visually clear treatment of the function concepts. It's not algebra, it's visualizing functions. And that's what these mapping diagrams are about. They're about visualizing function concepts, not about the graph, which is a very tight way to visualize a collection of ordered pairs. But this tight way fails when we get to functions of 3 variables. You don't draw graphs of functions of 3 variables. You don't draw, it's hard to draw graphs of functions of 2 variables, you've got to be in 3 space already to do that. But if you've been working with mapping diagrams all along, then when you talk about a function of 3 variables, all you need to do is set up, I'll do 2 variables first. So you set up 2 controlling variables, the x and y, and a third controlling variable, z, and you say, well, take a number here and a number here. So it takes 2 numbers on the where they are on the axes, and you send them into a feeder box, and out comes a number. And if you want 3 variables, you just put a third axis up. We want 4 variables, but now, in calculus, one of the things that's important is the derivative. And this is where I get a lot of my students say, well, that's really the way to think about it. All right? So when you're doing calculus and you think about, well, what's the derivative? Well, the derivative is local linearity. It's about a rate of change. How much change is going on here for a unit change here, even when you're small, or when you're very small. So local linearity. All right? So if I want to talk about z depending on 2 variables, well, we talk about the partial derivative. All right? So what does the partial derivative mean? Well, it means that I might keep the y fixed, say at 2, and this is up here at, say, 4.